All right, lads and lassies, here we are, stoichiometry part 3, where we're going to talk about percent yield. Before we do that, though, I want to give you a chance to practice what you've learned in the last two videos. So we'll take a look at this problem here. So go ahead and read through that. The balanced chemical equation is one we've already used. So we've got 5 moles of fluorine gas reacting with 2 moles of ammonia to produce 1 mole of dinitrogen tetrafluoride and 6 moles of hydrofluoric acid. So there's a series of steps that we've talked about. You want a balanced chemical equation, which we have. You want to identify your knowns and unknowns. You want to check the map to see where you're starting, see where you're ending up. You want to set up your game board, and then you want to perform your calculations and check your answers. So see if you can proceed through those series of steps, set up the problems, do the calculations, and pause the video while you're doing that. So we're going to start with our knowns and our unknowns. So we know we have 5.31 liters of fluorine gas. That makes F2 our known. And we are trying to figure out how many grams of hydrogen fluoride is going to be produced, or hydrofluoric acid. So that is your unknown. I'm going to check the map. The map, we're starting with volume on the left side, which means we don't need a molar mass for fluorine. We are trying to figure out how many grams of hydrofluoric acid is going to be produced, so we do need a molar mass. So again, you might take a second, calculate that, write it above the HF on your formula that should be written down on your paper, and pause the video while you're doing that. All right, we're going to set up our game board then. 5.31 liters of fluorine, the top left. Our first conversion is from liters to moles. And so, again, 22.4 liters of fluorine in 1 mole of fluorine. Then we're going to go to the mole ratio, 5 moles and 6 moles. So you might want to think about whether the 5 goes on top or on bottom. And of course, we're going to put that 5 on bottom because on that diagonal, we need the moles of fluorine to cancel out. We then need a molar mass of hydrogen fluoride, and that molar mass should be 20.01 grams in 1 mole. We're going to cancel out our units that cancel. Going to multiply across the top, we're going to divide across the bottom, and you should get 5.69 grams of fluorine. And if you didn't get that, go back, check your calculation, go back and check the setup, see if you can figure out where your errors were. Take a second, let this one all soak in, see if you can sort out what's going on here. Why is there only one color? Of course, because we all live in a yellow submarine. Okay, so the next topic we're going to talk about is percent yield, where we think about if we have a particular chemical reaction, there is an expectation for what we might be able to produce, but we sometimes find that, or often find, that what our expectations are and what we actually get are not the same. It's a perfect time to think about that for a little bit. But if you go back and you think we've been using the analogies of making cookies a lot, when you think about that analogy, we have this idea of there being a theoretical yield. A lot of cookie recipes will say they make something like 16 to 18 cookies, or I don't know, you pick a number, it doesn't really matter. The point is, we find that unless you make those cookies the exact size that the recipe intends and that every cookie is exactly the same, you rarely actually make as many cookies as the yield for that reaction suggests. So we have 3 concepts here, right? One's the theoretical yield, and that's the maximum amount of product based on a stoichiometric calculation. That's the answer you get from your game board. Theoretical yield has to be calculated. Your actual yield. Your actual yield is how many cookies did you make? It's the amount of product that results from any real chemical process. So this means you did the experiment, you measured a product, or if we're talking about kind of learning from textbook examples, then what is the actual yield given to you in the problem? So Actual yield has to be given, actual yield has to be measured, but you're never going to do a game board calculation or a stoichiometric calculation to get actual yield. Then what is percent yield? Well, percent yield is the comparison of those two things. What percentage of that theoretical yield did you produce? There are a lot of errors that can lead to this you not getting 100% yield on a reaction. Some of them are just inherent in the chemical process. Reactions don't go to 100%. There could be impurities, right? But your actual yield should generally be less than your theoretical yield. And if it's not, then you definitely have some impurities or you have some calculation issues because you cannot produce more than the reaction allows for. That's a violation of the law of conservation of mass. Okay, so we're going to look at this particular situation. So ammonia gas, which is a key component in chemical fertilizers, is produced by the Haber process, which just reacts atmospheric nitrogen, which makes up almost 80% of our atmosphere, with hydrogen gas under high pressure and temperature to produce ammonia NH3, which is a fairly critical feature of modern society. So we're going to look at the percent yield on the Haber process if 134 grams of nitrogen gas reacts with excess hydrogen gas to produce 188.6 liters of ammonia at standard temperature and pressure. As a side note, this Haber process has a really, really interesting history. And if you're looking for an interesting read in the history of chemistry, The Alchemy of Air by Thomas Hagar is all about how that process was discovered. And the interesting thing here, of course, is that there are two things you can do with the nitrogen byproducts of the Haber process, and that is you can make fertilizer to feed the world, or you can make bombs to blow a lot of people up. And both of those things were done. This was, of course, discovered around the time of World War I and leading into World War II. So there's a lot of historical context there. All right, so let's go back to this Haber process then. So take a second and come up with a balanced chemical equation for this process. Make sure you label your states of matter, and again, pause the video while you do that. Okay, there we go. So there's your balanced equation for the Haber process. Again, there's a lot of conditions that we would write above the arrows in terms of specific temperatures and pressures. And there are catalysts involved here as well. We're just going to go with the kind of base equation. You have two numbers, right? 134 grams of nitrogen gas and 188.6 liters of ammonia. And you have to decide which one of those things is your given piece of information. And where to start your game board. Well, you can't do a theoretical yield of a reactant. So nitrogen gas is one of our reactants, and so we're going to start with that to figure out how much ammonia we would expect to produce, and then we're going to compare that to what we actually did produce, which is 188. So set up your game board, do all of your conversions to go from grams to moles to liters of ammonia. I've done this all in one step here, so I'm going to let you take a second, pause the video, see if you can set up your game board and sort out your theoretical yield of ammonia, and then you can check your answer. So here's your game board on that. You're going from grams of ammonia to moles of ammonia. We'll do the mole ratio 2 to 1 to get ourselves to, grams of nitrogen is where we're starting, not grams of ammonia. 134.0 grams of nitrogen converted to moles of nitrogen. We're then going to convert the moles of nitrogen to moles of ammonia, and then moles of ammonia to liters of ammonia at standard temperature and pressure. That's 22.4 liters. And so that produces 214 liters of ammonia. That is your theoretical yield. That's the maximum amount you can expect to produce. We only produce 188.6 grams. So of course, you're actually producing a little bit less here. And so to look at a percent yield, the percent yield is actual yield over theoretical yield times 100%. And so you take that 188.6 liters divided by the 214 times 100, and that gets you 88.1% yield. Again, 3 significant digits because of the 214 liters that we got out of our calculation. And that's how you do a percent yield calculation.